Okay. So I think you now have a good idea of small world networks. Okay. So what are small world networks? Can you just tell me? So small world networks are one, local connectivity, high local connectivity, which is uh, characterized by clustering coefficient, okay, and then random links, okay, random links which reduces the diameter, okay, and the third is sparse. Okay. So these are the 3 points which we have identified. Okay, no problem. So these are the 3 points based upon which small world networks go. Okay. Now again I come back to the Milgram's experiment. So Milgram's experiments, all these 3 things, what does this 3 things show from Milgram's experiment? That the structure is something like this. Something like above. Okay. But in Milgram's experiment there was one more important thing which happened, more subtle, but is that people found others. Okay. People found the target. So how did people find the target? So people found the target by doing a breadth first search. Was it like that, that people, means I give it to the second person and he did a breadth first search and did it, or he had some local knowledge? He had 2 things. They see, he had some local knowledge and he had an idea about the proximity, his proximity from the target, his proximity and his local people's proximity from the target. So these are the 2 things intermediate person knew, or any person in the chain. The first person also had, number 1, he had some local friends. Okay, this local friend one can may be in America, that is okay, but second is that he had some idea, means local friends and proximity of these local friends from target. Okay. Okay. These are the 2 things they knew. So these are basically local knowledge. These are basically local knowledge. Okay. So the point is, not only the structure, the function was based upon a local knowledge, means on a local knowledge, even then people could find it in polylogarithmic time. Okay. Even then people could find it. Okay, I do not use the term polylogarithm, people could find it quite fast. Okay. So now let us see, let us revisit the small world model. We take a 2D grid. I think we told about it in the last class, but we take a 2D grid and we randomly means randomly put some long link. Means previously we are working on ring, but let us take a 2D grid and randomly put a long link. Okay. So this is say target, or this is start and this is target, something. Okay. It may not be this, it can be this. Okay. So now tell me what will be the algo to go from source to target. So, what is check or for each node, okay, for each node, okay, for each node visited by the message. Okay. When the message comes, what does a node do? Check all your neighbors say n, calculate proximity n and target. Okay. For all your neighbors, you calculate the proximity and send it to the neighbor neighbor n, I write small n belonging to the big set n, which is nearest. Okay. So, this at least what does this ensure? That it will reach. So, it is a non-decreasing function, the message will reach. Okay. But does it ensure that it will reach in polylogarithmic time? Yeah, because you can always construct some, or you can see that you can have come here, you can always go very means you can show that it may not be so fast. In polylogarithmic time means at each step you have to cover how much? If it is log n say, okay. So, at each step you have to cover, yeah, you have to cover some, okay, means you have to cover a portion of the yeah, a fraction of the nodes, means it is like this, that if it is, then you have to cover, if this is the distance, you have to cover ordered distance almost every time. Okay. Otherwise, you cannot reach it in log steps. Okay. Clear? So, the point is, if you do a flooding, then you will surely reach in log n time. But if it is just one step, a person is doing a one step just based upon this local knowledge, there is no guarantee that it will reach in log n time. Okay, or in logarithmic time. Because polylogarithmic means a log n square is a polylogarithmic concept. Okay, that is why I am using the polylogarithmic. So, is this, are we identifying a new problem? Tell me, are we identifying a new problem? Huh? Yeah. So, that was we have to see, means the point which I want to drive, that just telling that there is a small world does not guarantee that you can traverse the small world based upon local knowledge in polylogarithmic time. Okay. So, these are two level of problem. So, there is a structure problem, there is a function problem. Okay. So, obviously structure influences functions, but structure problem and function problems are two different problems. Okay. So, still now we are talking mostly about structure of complex networks. Now, we are talking function of complex networks. Okay. So, if you see the review paper, it is structure and function of complex networks. Okay. So, point is clear that it is not a structure problem, it is a function problem, but anyway structure influences function. So, now I build up the structure, which I think I told you in last class, that instead of putting this link randomly, if I take u, the other other point or other node of u will be chosen PUV is proportional to distance between UV to the power minus r. Okay. So, what happens is as r becomes high, what happens? DUV decreases, so the probability decreases. So, it is you have chance to have some medium size link, but you have less chance to have very high size link when r is positive. Okay. Clear? Okay. So, now so I have now imposed a structure. Okay, that is clear. I have now imposed a structure. It is not just random links, you are linking with here based upon the distance. Okay, clear? So, now the question is that how does R influences? So, now Kleinberg actually he had this paper in Nature, okay, navigation in small world. Okay. So, it was a Nature paper. So, it is very difficult for a computer scientist to have a Nature paper. Okay. So, that is why I just put it up. So, in this Nature paper what he showed is that if r is equal to 2, then only you can have a polylogarithmic time. Otherwise, for all r's r less than 2 and r greater than 2, okay, for all other cases it is some order n p, okay, or n L I write. Okay. So, it is polynomial time of L, where L may be a small number, but it is polynomial time of n. It is not polynomial time of log n. Okay. So, you have two cases where you have it is a polylogarithmic of n, and for all other cases you have to be log n. Okay. So, the point is clear. So, now what is the philosophical point behind it? Philosophical point behind it is that when r is very small, what is happening? So, when it is 0, it is uniformly random. When r is 0, it is random. So the link is random. When r is small, link is random, and when r is very high, say r is 50, then what happens? You can only have local links. Okay, when r is 50, you can only have local links. Okay. So, what happens is, so when you are building up long links, that does not have connectivity with the local links, okay, means then this long links cannot be used. Okay, when you have long links which does not have connectivity with the or connectivity means when it does not have any connection with the local links, this long links cannot be used. Okay. And if there is no long links, then things cannot be used. So, you need a well balanced long links, okay. You need a but that should somehow be related with the local links. Okay. Means like you can have a large NRI community, but your basic education system is not working. So, you cannot take advantage of the NRI community. So, you should have a balance between long links and short links. Okay. So, this is how things begin to behave. Okay, okay. I will write the equations first. So the point is, when it is r, you have delivery time as when r is, you have delivery time means this is anything I can okay, and when you have r greater than 2, okay. So okay, so it's like this, that this is just going by n, means if you take log, I have taken log. Okay. So what is happening, you say this way, if I write n, okay, so if I write order n minus r by 3, so if I take log, I am sorry, what was this, alpha n 2 minus r by 3. So take log, it will be 2 minus r by 3 log n. Okay. So that is why it's, you are getting a straight line here, and this way it is so that is r minus 2 by r minus 1 log n. That is why you are getting a curved line this way. Okay. And for this case it is log n square. Okay. I have taken that as a base for 2. Okay. So this is how the curve comes. So now let us think why this is log n square. Okay. If this has to be a log n square, what should be the intuition? So one important thing what we have said is that it is what is our local algorithm. First of all, tell again that you check all your links, local links and global links, and see whichever is the closest, switch it on that node. Okay. Clear? Okay. So it is a non decreasing function, that is again I am reiterating, but it is a non decreasing function. So now let us think that I divide, so this is the source, this is the target. So what happens, I say a jth phase, say I say a phase, each is a phase which is between distance 2 to the power j to 2 to the power j plus 1. I break up the nodes from, this is the source, this is the target. I break up the intermediate nodes into phases. Each phase is of distance, okay, from the target. Okay, I say it from the target. It can be from the source, but because I am trying to reach target, I will go that way. It will be A j is 2 to the power j 2 to the power j plus 1, the distance. Is it clear? So if now think, if I have a algo on which I step on each phase once, if I step on each phase once, at how many steps will I reach? I have an algo by which I step on each of this phase once, then how fast will I reach? Log n, because this would be log n, because I think this is n, let us think this is n, okay. Then this would be log n, there will be log n breakups. Okay. So, now, so that my problem reduces into two parts, is that given that I am in a phase say a j plus 1, I want to go to a j. Okay. See, you break, let us think, see n is equal to 32. So, 2 then 4 means first phase is 0 to 1, okay, 1 to 2, 2 to 4, 4 to 8, 8 to 16 and 16 to 32. So, how many? 1, 2, 3, 4, 5, 6. So, that is 1 plus log 32.
Yeah, but how do we know that how many nodes are in each phase?
No, that is what I am telling, that each phase is of this distance and this is a uniform grid. So, you can calculate how many nodes will be there, that will do, but you can always calculate that. But what you are telling, essentially think it from the distance point of view, you are traversing the distance. So, that would just take 1 plus log n steps. Am I clear? Okay. So, what am I trying to say? That I will try to find, given the distributed algo or the local greedy algo, given the local greedy algo, what is the probability that I will reach from phase 1 to phase I to phase I plus 1, or I was using the term j, so j plus 1, or it should be opposite, j plus 1 to j according to our convention. Okay. Am I clear? The point is clear? Okay. So, now let us, okay. So, I think I did not tell you some other important parameters. We can see this graph again and tell about some important parameters. One is p. What is p? P is the distance, the amount of distance you want to tell local. Okay. So, p can be, if p is 1, your locality is this one. Okay. With whom those nodes whose Manhattan distance with you is 1 are local to you. If p is 2, those nodes whose Manhattan distance is 2 is local to you. Okay. So, this is how p is the locality and Manhattan distance. Okay, locality and Manhattan distance. And what is q? Q is simply that you have q long links. Each node can have q long links. Q can be 1, it can be 2. Okay. Each node has q long links. Okay.
What do you links outside the locality?
Yeah, every node has some long links, so that's q long links. And we know r. What is r? R is the distance. So there are three parameters in this model. One is p, one is q, one is r. Q is number of long links each node has. Previously it was denoted by p, that given a short link, what is the probability there can be a long link in the Newman, Watson Newman model, if you remember. Okay.
So, and how will you define long link in this model?
This probability with this probability, that if I have a edge this way, the edge on the other way is determined by this probability. Okay. So this is clear. So you have three model parameters, p, q, and r.
So those two P are same or different?
No, so this is the probability and that is p. Yeah, I could have used a L something locality, but Kleinberg has used the term p, so I keep it p. Okay. Okay. The random links, small world has long links, small world have local links, and then it can have long links.
Would it be possible that a long link is a link that connects a node inside the locality to a node outside the locality?
And you can define it like that, but what we are telling, it's to a particular node. In fact, in essence it is, that's the essence of small world. It is linking something within the locality to something outside the locality, the links. Okay. So I hope it's clear. So the simplest model will be p is equal to 1 and q is equal to 1. Okay. And when we are, I use the star concept because to differentiate. So this is what we said. Okay. So we have to normalize it. What will be the normalizing factor? Okay. It is just a normalizing constant. So now let us try to I go it for 2, okay, minus 2 for the time being. So r is equal to, so we are trying to prove this for r is equal to 2, okay, why it is polylogarithmic. For r is equal to 2, why it is so for all the cases henceforth we are considering r is equal to 2. Okay. So now again come back to this model. So see how many neighbors you have at distance 1? 4. Okay. So at distance 2, 1, 2, 3, 4, 5, 6, 7, 8. So how many neighbors? It will be 4j. At j distance it will be 4j. At 1 distance 4, at 2 distance 8, it will be 4j. Okay. So now what I want to write is that so what happens is, see it this way, it will be 4j into 1 by j square, this thing. Are you agreeing that this thing will be 4j into 1 by j square? Because all 1 distance node, all 2 distance node, all 3 distance node. Okay. A jth distance node, how many nodes are there? 4j. Clear? Kaustubh, is it clear? In jth distance, how many nodes are there? 4j. So, what is this? Okay, I think I would write this thing once more. That summation d u v to the power minus 2. Okay. So, what is this? All ones 1 distance, all 2 distance, 1 square, 1 square, all 2 distance. Okay. And all jth distance, okay. And how many are there? 4j. In each group, how many? 4j. So, you can write it as summation 4j into j to the power minus 2. Okay. And j will vary from 1 to 2n minus 2. Okay. I will tell you. Okay. So, this will give me 4 into j to the power minus 1, and this basically gives me. So, this is again okay, I can write it as this. This will give us the, I can take the log, this is a log function and its limit is ln 2n minus 2. Okay. This basically gives us 4 ln e plus 4 ln 2n minus 2, which gives us okay, and which okay, 2e will be less than 6. So, this will be less than 6. Okay. Is it okay? Okay. Yeah, okay. So, what will be d u v? So, this will be 4 ln 6n d u means Okay.
So that should be an inequality relation.
Yeah, but this is an inequality. So, the upper limit of this probability is this, and the lower limit. So, means sorry. So, at least the probability will be this. Okay, at least. Okay, it's fine. Okay, now you take J. Okay, so phase J, where J is log n and log n. Okay, log n and log n. J can be highest is log n. Huh? We saw that J, if 32, then J can be highest is 5. Okay, no problem.
So, but also the upper bound of J to be 2n minus
J to be
2n minus 2. The summation
yeah
previously, right?
yeah.
The upper bound of J.
I will talk about that. So just let me go this way. Okay. Okay. Phase J is log n less than J less than log n. Okay. So, I am just seeing for this. What are the other phases there? That J is equal to log n, this one phase, and J and 0. Okay. In the 0th phase, the first phase, the second phase. Okay. So, let us just talk about this phase. Okay. So, now what is the question? What is the question we want to ask? What is the question we want to ask? I have told you already that you are at phase J. This is the target. Okay, I have drawn the now the picture inverse way. You are at phase J. You want to be at a lower phase or at a higher phase J plus 1. Okay, you are at phase J and you want to be at phase J plus 1. This is what. So,
J is the distance from the source node.
J is the phase.
Yeah.
If phase means what? It is 2 to the power J plus 1 and 2 to the power J. I have told you.
Yeah, that is fine, but what does it represent physically? Does it represent the number of nodes at a distance J from the source, or does it represent the distance itself from
It
the
just represents the distance. We will calculate the number. So, we have just formed a set. Think a phase means phase J. What we are using a word J and a phase J. Huh? What is a phase J? Set of all nodes whose distance is between 2 to the power J to 2 to the power J plus 1. Huh? We are talking about Manhattan distance. Distance here means Manhattan distance. AJ represents a set of nodes whose distance is between 2 to the power J and 2 to the power J plus 1. So, that is why all this represents A to the power AJ.
AJ is the distance from the source or the destination?
Target. This is the target. That is why I have drawn the picture now inverse way.
AJ is a set of nodes.
AJ is the set of
2
nodes.
power J is the distance.
2 to the power j to 2 to the power j plus 1 is the distance.
Then what is j?
2 to the power j is j. So, I am telling this is a phase j. No, no, no. Distance is j 2 to the power j to 2 to the power j plus 1. Distance.
Then j is just enumeration.
Huh.
J is counting 0, 1.
Yeah, j is enumeration. That is what again come to this, that what, how are you traversing? At first phase you are here, second phase you are here, third phase you are here, you are going like this. So, somehow you are crossing one phase at a time, where j is enumeration. Okay, it is correctly 0, 1, 2, 3, 4, okay, 0, 1, 2, 3, 4, 5. Okay, it is just enumeration. The distance, am I clear now? The distance is 2 to the power j plus 1 to 2 to the power j, and aj is all the sets with distance dj. Now, it is clear, all the sets with distance dj, not with j, with distance dj. Am I clear?
So how can you have a distance in exponential? You can have a linear distance. Like if you actually finding a Manhattan distance, you have j, j plus 1. That's how you actually grow. And the number of nodes in that
No,
particular.
no, you have a linear distance, but if you don't, the point is what, you want to come in logarithmic step. So, if you want to come in logarithmic step, you what, there can be two ways thinking, that divide the entire thing into log areas. See, okay, let us think this way. So, you have 32. So, what is log 32? 5. So, you can divide 32 divided by 5 is 6.4. So, you can divide it into 1, 2, 3, okay, 4, okay, 1, 2, 3, 4, 5. Okay. So, first step you go here this way, this way, this way. So, this is one way of thinking.
What is 32?
Huh?
What is 32?
32 is n.
N is what? Number of nodes.
Number of nodes. N is number of nodes. So, and you want to traverse this, you have to start from here and you have to go here. You have to start from here, and what is one technique? One technique is go log n's each time. At each step you have to cover at least how many? N by log n nodes. You want to reach it in log n steps. From here, from 0 to 32, you want to reach it in log n steps. At each step, how much you have to cover? If you go uniformly, n by log n. Am I? Or what you can do, that this log n steps can be divided in this fashion which I am doing, that in the first step you go 1, second step also 1, third step 2, fourth step 4, then 8, then 16.
Essentially, the structure of the graph is different.
Now, structure of the means you have to, your idea is you have to traverse it into log n steps. You can traverse it in any way. So, this is the way which I am proposing for my analysis. In reality, people can do anything else, but in analysis, I am trying to, what I am trying to achieve? I am trying to achieve that can I reach within log n steps. Okay. And my idea would be that I can reach within log n steps, this is number 1. Number 2 is, if so, this is a phase, okay. So, I want to go from one phase to the next phase, that is my idea. I want to go from one phase to the next phase.
So there 8 is the number of nodes in that phase.
Actually, there is one more thing, this is a two dimensional thing. So, 8 is just the distance and number of nodes are all nodes which distance 8. So, here what you have a two dimensional concept here. Yeah, yeah. So, if I do it draw this, it's the same thing. So, this is 0, 1, 2, 4, 8. So, this is what is 4, but number of nodes are all this. Okay. So, is the premise clear or should I tell you once more? I know this is little non-intuitive, but okay. So, I want to traverse in log n, I divide this log n into this way, okay. So, that initially I cover less, later I cover more. It is like that if the pond is half filled in 9 days, in how many days it will be fulfilled. Okay. The same concept. Okay. So, what happens is, this part was clear. So, now let us think that when I say that I come from this to somewhere in between, okay. I come from, this was what we were telling, that I come from phase j, this is the target, I come from phase j to phase j plus 1. Okay. So, but I can think that is phase j plus 1 essential, or if I can come in phase j plus 2, is it a problem? If I come in phase, it's better. If I can skip, it's better. So, now the probability, what you have to calculate is the probability that from this phase j plus 1, what is the probability that you will reach phase k, where k is greater than equal to j plus 1. So, instead of just thinking one step, I think entire step. Yeah, I do not know long link or short link. Anyway, I want to come from here to somewhere inside. I do not care whether I come here or here or here. Anyway, if I go deep inside, I am better. Okay. So, now let us calculate how many nodes will be out here? Can we calculate how many nodes will be out here? Can you calculate? Okay. So, okay, I again tell, if I know how many nodes are out here, so let that be bj, I will calculate later, let that be bj. Okay. And so, how many nodes will be out here? So, this is all 2 to the power j plus 1 to 2 to the power j. Okay. 2 to the power j plus 1 to 2 to the power j. Okay. Now, think that what is the distance this any node has to traverse to reach here. What is the distance any node has to traverse to reach here? It will be 2 to the power j plus 1. Okay. Okay, since there is less time, I just tell and we will talk again. So, how many distance will be there, and then what we can see that from here to come here will actually take something like 1 by 128 ln 6n. Okay. 1 by 128 ln 6n. Okay. And then what we think, okay, then what we think is that so what we go get that the probability that it will reach from here to this point, okay, and that you get something like that. Then you go on finding the expectations, the expectation that it will reach from one step to the next step, and that expectation again you get 128 ln 6n. Okay. So, what is the expectation? The expectation that you reach from one phase to the next phase is logarithmic. And how many phases are there? There are logarithmic phases. So, then it becomes that time to reach is ln square. Okay. So, again I tell you the, let us have the premise clear, I will tell you the detailed calculation next class. So, the first thing is what is happening is that the idea would be you have a target, okay, I draw it again in a simple way. So, you have a target node, this source node, and you are coming to the target. So, and you have this some distance n, okay, you have some distance n, and you want to traverse, you want to break this distance n into log n partitions. Okay. You want to break this into log n partitions. How can you break this into log n partition? One method is uniformly have this partition. I want to make it partition based upon distance. One would have been just n by log n. The other is, the first is just distance 1, the second is distance 2, the third is distance 4. This way you go on. Okay. And as you come inside, the distance increases. Okay. So, what happens? You have a phase j is all nodes which has a distance between 2 . Okay. And now, what you show that to cover each phase you take a log n time. So, you have log n phases and each phase takes log n times. So, that is why the time complexity becomes log n square. Okay. So, what we have to show is that why it takes log n times. I think everything else is clear, only thing we have to show that why you have to go from here to here in log n time. that we will do in detail next class. So, tell me, is the premise clear now, or any problem is there? Okay. So, next class we will continue this and we will show why this takes log n times and other does not.